Okay, so as I was saying that this lecture would be more on the problem solving, and later I'll be explaining the ideal regenerative Rankine cycle. So let me come to the first question. So here the question says that a thermal electric power plant produces 1000 megawatt of power. If the coal releases 900 into 10 to the power 7 kilojoule of heat, kilojoule per hour of heat, then what is the rate at which heat is rejected from the power plant? Simply we know that the what is the work done by the electric power plant. We know what is the heat supplied to the power plant. So yeah, as you can see, um, so as you can see in this figure right to the right, so in a basic power plant, if you can see that the a particular source will supply the energy to the system, and it will be utilized, some amount of it will be utilized in developing the work, and the other will be rejected to the sink, which is actually the ambient. So the QS, okay, let me solve it. So the heat supplied from the source, that is the QS, it is given as 910 to the power 7, and we will convert it into megawatt, and it would give us 2500 megawatt. So the work produced is given as 1000 megawatt. The net heat rejected to the sink will be given like this. So that will be 500 megawatt. I think everyone might have got this. It is a very easy question. So moving on to the next. So what will be the equivalent evaporation in kg per hour of a boiler producing 2000 kg per hour of steam with enthalpy content of 2426 kilojoule per kg from feed water at temperature 40 degrees Celsius. So basically it is asking it has given how much steam is produced per hour, that is 2000 kg per hour, and the enthalpy content of 2426 from the feed water, and the feed water is taken from 40 degrees Celsius, right? So the properties at 40 degrees Celsius, that is liquid enthalpy and enthalpy of evaporation, is also given. The enthalpy of evaporation at 100 degrees Celsius is 2258. So using these properties, you will have to say what is equivalent evaporation. So before moving on, I would like to explain what is equivalent evaporation. So equivalent evaporation is the rate in kg per hour at which water would be vaporized in a given steam boiler if supplied and evaporated at the normal boiling point and normal atmospheric pressure. So let me explain you like this. Our steam, the boilers are operating at a very high pressure, right? So you might be seeing this, the red color curve. This is actually the actual pressure application in a boiler, and accordingly it is evaporating the steam. So if we are to compare this red color curve to the ambient situation, when the water at a saturated condition at 1 atmospheric pressure, it is simply getting the latent heat of vaporization and getting converted into saturated steam. So if only this process is happening, so how much mass flow rate at this particular condition should be the result to match the two processes? Are you getting it? So basically there will be a mass flow rate of the steam which will be um, supplied by the boiler, and it is working in this particular curve with this particular process, as you can see. And if we are to compare the same amount of energy, uh, but at a 1 atmospheric pressure conditions, then how much would be the mass of steam that it would supply at this 1 atmospheric this condition? That would be the equivalent evaporation. So basically this energy says the energy of steam at elevated pressure conditions in the boiler would be equal to the energy of evaporation of water to steam at normal boiling point, that is 100 degrees Celsius, right, at 1 atmosphere, and at the atmospheric pressure conditions. So like this I will equate the ms is the mass of steam which is at the elevated pressure conditions. This is hs minus hw. Hs is the enthalpy of the steam, so we are given the enthalpy of the steam is 2426, and the enthalpy of the feed water, so it is the feed water is coming at 40 degrees celsius. The feed water here liquid enthalpy is given as 168 kilojoule per kg. So that would be the energy of steam at elevated pressure conditions inside the boiler. And on the right side we have the equivalent steam flow rate, and which is only getting the latent heat at 1 atmosphere, and the entire latent heat. There is no superheating, neither there is any wet steam available. So that would be the total hfg at 1 atmosphere, which is given as 2258 kilojoule. So equating, we will get the ms dash, that is 200 kg per hour. Basically I would say that in so this is a very hypothetical question. So normally you would see that the enthalpy, sorry, the equivalent evaporation rate would be larger than what is the steam, at which rate the steam is being produced by the boiler, because the enthalpy difference between the steam and the water would be very high. And when we compare that with the normal pressure conditions, normal conditions at the 1 atmospheric pressure, then we will find that it should the more amount of water or steam should be produced at the 1 atmospheric condition in order to get equivalent mass flow rate at higher order actual boiler conditions. That is why you will find actually the rate should be very high, but this is a hypothetical question. So here you are getting the equal rate. Normally it should be higher. So I hope you have got the concept of equivalent evaporation, which was taught in the lectures. So now moving on, is there any question? So if there is any question, please do not hesitate, you please ask. Okay, so the next question. So this in our class we read about the use of economizer, right? How economizer will be means it increases the efficiency of the whole boiler setup. So how it does is that it supplies the sensible heat. So the feed water will be in the indirect contact with the flue gas that is escaping the boiler setup. So when the feed water comes in contact with the hot flue gas, it will get some energy from the flue gas, and we do not want the flue gas to escape at very high temperature. That would be very inefficient. We need to use the whole of the energy of the flue gas, so we will need to decrease the temperature of the flue gas and utilize it in other applications, such as increasing the energy of the this feed water, or increasing the temperature of the feed water. So we actually, the sensible heat is being provided by the economizer out here. You can see here in this application. So this is a boiler application. Normally the boiler would have uh, provided this sensible heat, but now the economizer is supplying that heat. So the amount of heat to be supplied inside the boiler, if it is constant, then the mass of the steam produced would be very high, right? So the output would be very high from the boiler. So accordingly the economizer is used, and this is the question related to the economizer. So the question, it says that a boiler produces 2000 kg of dry and saturated steam per hour at 10 bar, and feed water is heated by an economizer to a temperature of 110 degrees Celsius. So now at see here it is given that 200 kg of dry and saturated steam. Okay, so here it is 200. Since it is dry and saturated steam, we will not extend this curve in this vapor region, because it is not superheated, it is dry and saturated. So this is the end point of the boiler, end state of the boiler, steam inside the boiler. Then again it is saying that an economizer is elevating the temperature to 110 degrees Celsius. So till 110 degrees Celsius it is supplying the heat, and from here from water to directly to the dry and saturated steam, it is getting the heat from the boiler. So again a net amount of 225 kg of coal of calorific value of this 30,100 kilojoule per kg are fired per hour. So we know the rate of coal being used per hour, and we also know that the 10% of coal remains unburned. So that is a very practical condition. So 10% of the coal may not be burnt during practical conditions. So now we will have to find we have to calculate the mass of the steam produced per kg of coal actually burnt, and the thermal efficiency of the boiler respectively. And it is given for 10 bar, the enthalpy, the Hg is given as this 2776.2 kilojoule per kg. Specific heat of water is given. Okay, so now how to calculate it? First we will so here nothing else is given, right? So we will directly, it is being assumed that the economizer is directly responsible for the whole of the sensible heat, and it is heating up to 110 degrees Celsius. That is why I have extended this curve, sensible heating curve, till this point. Okay, then the heat contained in 1 kg of steam in boiler. So at this point HF1, if we need to calculate the heat contained, so we'll have to directly calculate the state, this Cp into T. So we know the specific heat capacity into the temperature, that will give us the enthalpy at this particular point. And since we are calculating everything per kg of system, so we are just putting this as 1. So HF1 will be 4.18 into 110, that this much kg kilojoule per kg actually. Next we will calculate the total heat given to produce 1 kg of steam in boiler. So total heat that is being supplied by the boiler to convert the water into steam, that will be from this particular state to this particular state, right? So this is vapor state, so that is Hg, and this is HF1, that is feed water at liquid state but at the boiling temperature. So we will just simply subtract it, Hg minus HF1, and accordingly we will get the heat given to produce 1 kg of steam in the boiler. Then we will calculate the mass of coal actually burnt, that is MF equals to 0.9 into 225. Why 0.9? This is 90% of the coal which is burnt, 10% is left unburnt, right? So that would give us 202.5 kg per hour, since this was kg of coal per hour it was burned, right? So this will be per hour it will be burned. Then so our first objective was to find the mass of steam produced per kg of coal that was actually burned. So simply we will divide this is the amount of steam being produced, this is the amount of coal being burned, and so accordingly we will get this answer. Next is thermal efficiency, right? So thermal efficiency, so what is the total amount of heat being given by being received by the water in the boiler and divided by total amount of heat being supplied by burning the coal. So there might be lot of losses in the boiler, right? So the flue gases, it means there are a lot of losses, you might have read in the lectures. So according to that, the total amount of energy being produced by the coal, burning of the coal, will not get directly transferred to the in the production of the steam. That is why we will divide this and get the thermal efficiency. So ms into hg minus hf1. So we will already calculated what is the net energy supplied per 1 kg of steam. So this into the total amount of steam being generated, so that will give us the total energy, and accordingly the total amount of coal being burnt into the calorific value of the coal, and we will get finally it is 75.9% efficient. So a boiler with 75.9% efficiency, actually it is not that good. It should have been higher than 90%. You must have already heard that from sir in the lectures, right? So it is a low efficiency, and there are other accessories also, like air preheater, then superheater. So accordingly these are used to increase the efficiency above 90%. Now, so here this is one more question. So here it is said that dry and saturated steam at pressure 11 bar is supplied to the turbine and expanded isentropically to the pressure 0.07 bar. We need to calculate the heat rejected and the heat supplied and the theoretical efficiency, thermal efficiency. Okay, may I ask if I am audible, or I am somehow cut off? Would anyone respond, please? Audible. So, is there any doubt till now, or I am explaining very good? So I do not think the later is possible. So, is there any doubt? Please do not hesitate. Okay, okay. Okay, so there are a few questions related to this type of problem in the assignment. So I think putting up such questions here would help you solve the assignment problems, right? So here it is being asked to calculate the heat rejected, heat supplied, and the theoretical thermal efficiency. So the heat is generally rejected in the condenser section. So this is the condenser, 2 to 3 is the condenser. Here the heat is rejected to the ambience, or whatever the condition is in the whole Rankine cycle. So and the heat is supplied in the boiler, right? So from burning the coal or using other fuels. So that is how the heat is being supplied. The work is being done in the turbine 1 to 2, and some part of that work is utilized in increasing the pressure from point 0.3 to point 0.4 by the use of pump. So this is the simple Rankine cycle. Now we need to calculate the heat rejected and the heat supplied according to the conditions that is given, that is the steam at pressure 11 bar. So this the boiler is producing steam at 11 bar, and so the inlet 1 is at 11 bar, and the conditions according to this we will have to see the steam table corresponding to 11 bar. So I have already given you the values here in this 11 bar according to 11 bar, and the according to 0.07 bar. And let us go through the problem. So heat rejected basically is H2 minus HF3, because the condenser section is only this is the condenser section, and we'll be using this method to find the unknown H2. So you might be knowing that H2 is not being provided, it is a wet steam condition. So we need to first evaluate the what is the value of H2, and after that only we can calculate this heat rejected, because we know the value of HF3 according to the pressure 0.07 bar, and this is saturated water condition. So we will directly get the SF3 at this is the value, but we do not know the value of H2. So to calculate the value of H2, first we'll have to find the quality of the steam. We do not know at which how much wet is the steam, right? How much moisture is contained in the steam. So we will have to first evaluate it. And how can we evaluate it? So isentropic process. So this 1 to 2, that is the process in a turbine, and it is being assumed that if there is no heat loss from the boundaries of the turbine, then this is a reversible adiabatic process or isentropic process. So in an isentropic process, this is a vertical line along this entropy. So at a constant entropy, S1 will be at a constant entropy, S2 will be at a constant, and these two will be equal. So this is a vertical line, and we can equate these two like this. S2 will be equal to the SG1, and S2 will be, and we can also write the S2 as SF3, and the remaining X into SFG. So here till now, till here we know the entropy of the water, and till here we will just take the fraction of how much is the this length of the process, or means how much is the quality of the steam, how much. So from that we will get the entropy, and we know the values of SF3 and SFG. We just do not know the value of X. So equating this with SG1, this SG1 and here, so we will get X as 0.776. So this is the process generally applied, and you will also find it applied applicable in other this gas turbines and everything. So this is a very normal process, and it is mostly applied in all these thermodynamic cycles. So it is a very good trick, and you can use that to solve the problems related to that. Then after using the quality of the steam, means evaluating the quality of the steam, we will find the enthalpy H2. So how it is calculated? Till here we know the enthalpy of the water, and after that we need to calculate how much is the enthalpy till here. So if we can add this part of the enthalpy to this enthalpy, so we will get the enthalpy of state 2. So that is what we are doing, HF3 plus X into HFG. So HFG is the whole line means still liquid state at this point to saturated vapor state. So this is the whole HFG, and we are just using the part of it. So accordingly we will get H2, and then we will calculate the heat rejected as this H2 minus HF3. This is the heat rejected. Then what is the heat supplied? So the heat supplied will be given as Hg1 minus H4. So we know this is Hg1 and this is H4. Through this we are increasing the energy of the feed water by supplying the heat from the this coal burnt inside the boiler. So the 4 to 1, since no economizer or preheater is used, or even superheater is used, right? But separately we are not analyzing it, we are considering that as a part of the boiler itself. So 4 to 1 is the total heat supplying process. Then here we will just get the difference between Hg1 and H4, so we will get the heat supplied. So how to calculate? First we will have to find the unknown H4. Again, H4 is unknown, but we know that this process is through a pump, right? So from 3, the feed water, saturated feed water at 3 should be pressurized to get to this particular pressure 4. So this is the this is done through the pump, and the pump work, since it is an external work, we will have to use this equation VdP, right, minus VdP. So here since we are providing the work, it will be expressed like this, Vf3 into P2 minus P1. So P2 will be the final pressure, that is 11 bar. P1, it is 0.07 bar. So using the equation of Vf3 we know the value, we know Vf3 from the steam table. Then using this particular equation we will get the pump work, that is 1.093 kilojoule per kg. Please take care of these units, because somewhere it will be given as a megapascal, so you will have to work it accordingly. Somehow you need to get it converted to kilojoule per kg. So This is a common mistake in solving this kind of problems. Then we will find the enthalpy using the value of pump work. So that will be hf3 plus wp. So hf3 here, and we have externally provided some work, and we will hence the enthalpy is increased of the feed water. Enthalpy is increased to state 4. So that will be hf3 plus wp, and this is the value. Using this, we'll finally get the value of heat supplied, that is hg1 minus h4. So accordingly we will get this particular value. Then we'll calculate the theoretical thermal efficiency. So thermal efficiency is given by work done per heat supplied, and work done, since we know that this is a closed cycle, we can use the first law, right? So work done can be given as the del the in a reversible cycle, sorry, in a cyclic process. So the net exchange of heat will be equal to the net exchange of work, right? That is the first law. So according to the first law, we will calculate the work done, because the net exchange of work will be equal to the net exchange of heat, and the heat exchange will be that is the heat supplied here and the heat rejected. So this will be the difference of these two values, right? So accordingly we will get this particular value, work done. Then we already have the value of heat supplied as this, and after that we will just divide these two values, and we will get the thermal efficiency of the whole Rankine cycle at working at this particular pressure conditions, right? But suppose if you do not means if the part of heat rejected and heat supplied was not asked to be calculated, then how would you have gone through directly in calculating the thermal efficiency? So I will talk about that. So alternatively we can do this, that the amount of work done will be the difference between the turbine output and the work supplied to the pump, right? So this particular is the turbine output, work done by the turbine, and this is work done on the pump. So we will subtract these two values, and we know the end states. So 1 is known, 3 is known, but we do not know 4 and 2. So accordingly we will have to calculate the states 4 and 2, and we will use the methods which was discussed before. And after that we will get the value, and you see that even by this you are getting the exact same value, 745.49, and this is 745.497, exactly the same value you will get. So either you use the first law, or you use simply this, whichever way you are comfortable, you can get the thermal efficiency. So next, till now we have discussed a few problems which would I hope that it would help you in solving the assignment problems. So next I will discuss about the ideal regenerative Rankine cycle. So ideal regenerative Rankine cycle, it is basically a modification of a simple Rankine cycle. So as you can remember, in a simple Rankine cycle, so this is the schematic here, but this is the TS diagram. So here you can remember that in a simple Rankine cycle it was 3 4s 5 1 vertically to 2s and then to 3, right? But here we are modifying it to utilize the heat which is being rejected at the turbine. Okay, the heat rejected at the turbine is being utilized in increasing the or supplying the sensible heat of the feed water till the boiler input. So this particular curve, straight 1 to 2s curve, will get changed to 1 to 2 curve, like this curved. And where this particular energy is being supplied, this particular energy is being supplied to this part. So 4s to 5. So 4s to 5 was what? 3 to 4 was the pump work, and after at the outlet of the pump, this is the state 4s, right? So from 4s the feed water has to be sensibly and the temperature should be increased sensibly, so sensible heat must be provided in order to get the saturated water condition, that is 5, right? Normally the boiler itself provides with the sensible heat, but we are utilizing the heat being rejected at this turbine into providing the sensible heat. So this part of the energy is being utilized in this. The schematic here also says the same thing. So this is the boiler here, and the boiler output goes to the turbine. Now normally the turbine output would go to the condenser out here, the condenser to the pump, then pump would again supply this to the boiler, right? Normal simple Rankine cycle would do that, but here we do a modification that the exit from the pump, it is again being uh, kept in contact with the external body of this turbine. What happens in the turbine when the steam is expanded? So steam, when the steam is expanded, some heat is being lost to the uh, external body of the turbine. So in practical conditions you do not have a reversible adiabatic condition or isentropic condition, the heat is always being lost. So why not use that particular heat, the heat of expansion, right? So heat of expansion is being utilized now by the feed water at this point. So it is already getting some heat, it is getting heated up sensibly to the saturated water condition, and the saturated water condition, that is a state 5, is being again supplied to this boiler. So the purpose I have already explained, to reduce the sensible heating of the feed water by the boiler. So boiler does not have to provide the feed water, right? Then it increases the mean temperature of heat addition. How? So basically we provide temperature at this saturated conditions, uh, and increase the state of from the saturated conditions to the superheated conditions. So we use a superheater at the boiler. Now we do not have to use that. Generally the superheater is used in order to increase the mean temperature of the heat addition, but instead we are supplying this, we are reducing the amount of heat addition to the feed water. So by that process also we increase the mean temperature of heat addition. We do not have to supply a lot of heat uh, from the boiler. So that actually increases the efficiency, the ideal regenerative cycle. This I will show you, the ideal regenerative cycle has the same efficiency as of the Carnot cycle. So this is a very interesting fact. So it increases the efficiency by the but the drawback is that the net work output of the cycle is less than a simple Rankine cycle, obviously, because the total enthalpy change between in the turbine, it is now being reduced, right, by the heat extraction. So the net output will be reduced. Now let us please. Reheating. Mm-hmm. Yes. 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 Generally, the ideal optimal condition of reheating would be the by setting the optimal conditions, you will increase the work output, net work output. But huh. Yes. Yes. So the efficiency is actually the ratio between the amount of work output and amount of this heat supplied. So if the ratio is somehow increased, means we are increasing the work output at a very low amount of means comparatively low amount of this heat addition. Yeah, the heat addition should be always higher, and nothing can be more than 100%. But yes, suppose we are getting we have the same heat addition but we are getting more work output, then it is having higher efficiency. But higher work output may be sometimes required in practical conditions, but that might not means always mean that the efficiency is higher, because suppose you need the more work output, so you will have to extend this process 1 to 2 ways. So you will have the one point should be somewhere here, or you will have to this superheat, go to here and then again come to here. So in that you are also increasing the heat addition, right? You're increasing the heat addition in order to get more work output. So the overall scenario, what is happening is the ratio is somehow decreasing, the efficiency is somehow decreasing, although you are getting more work output. So that is the difference between work output, maximizing the work output, and the thermal efficiency. Huh. Efficiency ratio will decrease, but there are other conditions also, like regenerative feed heater. So this is some modifications of Rankine cycle. So based on that, they are increasing the this efficiency also. So huh. Hmm. Reduces, right? Efficiency increases, right? So yes, 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 yes. Mhm. Boiler pressure. Why do you think the boiler pressure will increase? Hmm. 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 But we are not using additional pumps now. We are actually using the state 3 was the inlet to the pump. That's a state 3. So state 3 to state 4 is only increasing the pressure of the pump. It is supplying, but the route of supplying the this feed water to the boiler is now changed. It is actually flowing through this instead of flowing directly to the boiler. So we are not increasing the pressure. It is sensible heating is actually increasing the heat of the water at constant pressure, right? That is why you use the specific heat capacity, this CP, right? So that is used only when there is a constant pressure application. So this part is constant pressure application, not we are not increasing the pressure here. Okay. Hmm. If you increase the boiler at higher pressure, means then your curve will change, right? So it will go here, it will come here, and your if you supply the same amount of work, then the end point of this will also change. Accordingly, your whole system will change, right? Maybe the end conditions will be here. Means if you are expanding it to a constant pressure, then the curve will come out here, then again it will go out here. So the whole thing, everything you will have to change accordingly. Is hmm. Boil for that hmm. expansion expansion, right? Expansion, okay, so hmm. Hmm. Okay, so it will shift to the left, I think, the quality of the steam will be a little bit lesser if you huh. Hmm. Hmm. For the same temperature, then it will shift to the left now. Then it will shift to the left, because you see this is a constant temperature, and this is a saturated condition. Let us talk about the constant temperature line out here. Suppose we extend it to here. Okay, suppose you consider it on my cursor, right? Okay, so here we would have the superheated state normally. So what we did is that we increased the pressure, but we need the same temperature. So somehow the pressure would be out here, right? The saturated condition will be out here, the superheater will only increase till here. in order to get the constant temperature, right? So it will come down here, otherwise it would have come out here. The quality would reduce at the exhaust, exactly. Okay, that is a very good question. Okay, uh, so till here I think, is anyone having any other doubts? So if it is clear, then we can proceed. So yes, yes. Install capacity. Okay. Install capacity. Okay. Install capacity, I will have to look through the term. I do not recollect at this moment, but maybe it is the capacity of the output work. Maybe it is the turbine work and the net work would be some so adjusted so that it produces that amount of work. Install capacity, I will again have to go through that term. Maybe I will answer to you in the discussion forum. Okay. Okay. So moving on, let me explain you the thermodynamic processes. Okay. So let me go through a little bit quick. uh, what happens is that here the process is 4s to 5. The 4s to 5, it is a sensible heat addition, and 1 to 2 is the work output. So since it is extracting the heat from this turbine, so this amount of this curve, the slope of this curve would be exactly similar to the slope of this 5 to 4s, because the because it is taking the same amount of heat. So yeah, this you can see this whole area. This area indicates T del S, right? The area indicates the amount of heat being extracted. So if we consider a reversible process with perfect insulation, then the amount of this area will be same as this area, right? So that is why this curve and this curve would be almost identical. So that is why uh, so this is one of the fact, and for ideal condition. And then the processes would be of heat addition and rejection would happen at constant temperature. Now why that? Because now here you can see that 1 to 5 is the heat addition process. It is happening at temperature T1, and T2 will happen at this 2 to 3 process is heat rejection, and it will happen at temperature T2. So these two are happening at same temperatures. So further we can deduce that the heat added from the external source, that is Q1, this part, is H1 minus H5, simply because the sensible heat part is not being supplied to supplied from the boiler. It is being extracted from the turbine. So that is T1 S1 minus S5, and then the heat rejected to the external sink will be same as T2 constant, and entropy difference is S2 minus S3. Okay, so we got that. Now in since the process is reversible, and we let us recollect this particular formula. So the S universe is the sum of the feed, the entropy of the feed water, also the entropy of the steam, right? But since the process is reversible, there is no net increase of the entropy, so that would be amounting to 0. So by that we will get the S feed water is equal to minus S steam, and accordingly we will get this particular formula: S5 minus S3 equals to S1 minus S2. Then rearranging, we will get S1 minus S5 and S2 minus S3. Now you can look at this: S1 minus S5, this is S1 minus S5, again S2 minus S3, this is S2 minus S3. So these two values are same. Okay, but the temperature, yes, it is multiplied by T1 and T2 separately, so these are different. And efficiency was given as 1 minus Q2 by Q1, right? So Q1 minus Q2 would be the work done, and divided by Q1 by this dividing it, we will get this equation. So further we put the values, and we will get 1 minus T2 by T1. So you might recollect now that this is the exact efficiency of a Carnot cycle. So this is having similar efficiencies now. So by using the steady flow energy equation for the turbine, we also get that H1 minus WT. So this is H1. So the WT work done is being extracted. So minus WT, then minus H2, that is the end condition. So we only need to consider this now. So minus H2 and H4 minus H5. So actually H5 minus H5 minus H4s is the amount of heat being extracted from the turbine. So we'll have to minus that heat extraction out here. So minus H5 minus H4s would give us H4s minus H5, right? So this would be the steady flow energy equation, and it would amount to 0. So from this we will get the turbine work as H1 minus H2 minus H5 minus H4s. So this has been referred from page 57 of Pikenag book, Power Plant Engineering. So this is the third edition. So this is a very good book written by a retired professor of Pikenag. So you can follow it for further reference. And by this we come to the end of this today's lecture. So are there any doubts? Yes, sure.